Hi everybody, my name's Chris Collison. So we've more or less wrapped up the course, and so it makes sense at this point just to go back and tie it all together. And really the context of the course is, well, you know what, we don't really do quantum mechanics anymore with a pen and paper, but when we start to work with computational software such as perhaps Gaussian or Chem3D or some commercially available quantum mechanical chemistry software, we kind of want to have an idea of what's going on under the hood. We want to have some basis to understand how to go further in our chemistry using quantum mechanics. We also want to think about how quantum mechanics ties into spectroscopy, which we use all the time to fingerprint the materials that we develop in an organic synthesis lab. So we'll keep those things in mind as we move forward. But again, the purpose of the course really is to really start to get an understanding so that all these things make sense as we look at spectroscopy and as we look at, for example, molecular orbitals and geometry, and we think about how synthetic procedures might be influenced, say, by shining light on a particular material. So we'll jump straight in at the early historical information from chapter 1, and we'll move through and try to put this all together, almost as a checklist as well for your upcoming exam. So thanks for listening, and we'll see you at the end of the presentation. So we're going to start by thinking about chapter 1 of McQuarrie. And our story really starts with a historical picture. So what needed, or what prompted the need for quantum mechanics? This dates back to the very early 1900s. So we have something called the photoelectric effect. And the idea there, of course, was that light would impact upon something like sodium metal. And what would happen is, as photons came in to hit the metal, we would have electrons that would be ejected. And we could tell that electrons would be ejected because there would be an increase in current. So this was an electricity measurement. And it turned out that when you increased the frequency of the radiation above a certain threshold, it was only then that you started to get electrons that were pulled out of the atom. And if you were below this certain threshold, you could turn up the intensity and nothing would still happen. So the outcome of this was that really photons were in existence. And, this tied in with something that Planck later came up with, or actually earlier came up with, associated with the ultraviolet catastrophe. But we have packets of energy in here associated with this amount of this energy, h times nu. So the frequency was associated with the energy, but the Planck's constant told us about how much energy was in each individual photon. And it was basically one photon per electron. And those were the interpretations of the photoelectric effect by Einstein. So it's worth reviewing that. The second thing that prompted the need for quantum mechanics was the ultraviolet catastrophe. So if we're thinking about future exams, we don't need to really think about the Rayleigh-Jeans law, which was proven to be incorrect or insufficient to describe black body radiation. But a qualitative understanding is valuable here. And again, it was Planck and the Planck's constant and an idea of quantization, so packets of energy, and basically having enough vibrations in resonance to generate a photon with a large amount of energy that would be in a photon of ultraviolet radiation. So again, a basic understanding of that works well. We also talked about the line spectra, and at that time, this is kind of like the idea of a strip light. So your fluorescent light bulb, and you've got it's hooked up to a voltage, right? So some kind of battery that goes around this system, and light comes out, right? So we get these photons of light that come off, and there were certain positions in frequency, certain energies. Now that we understand that because of the Planck's law, number of quantization of energy in a photon. The Rydberg equation at the time gave an understanding of where those positions would be. So there was some graph of frequency here, and we'd see certain lines that would show up, and the positions of the lines seemed to be associated with a 1 over n squared term that really described the positions of these peaks. And we now know, after solving the Schrodinger equation, that n squared term comes out of the math through quantum mechanics. So those were the three things that prompted the need for quantum mechanics. So review those. We also had Niels Bohr had two assumptions in here, and those two assumptions were that angular momentum is quantized, and I say in here now how true this was. We know that is very true now. So we think about L sub z, right, and we think about L squared as being quantized, and we now have operators for those two, right? So we have these operators that we've been talking about in later chapters of the textbook. So angular momentum is quantized. This was an assumption by Niels Bohr. And also Niels Bohr came up with an assumption that the transition energy would be quantized between electron orbits. At that time, the idea was that these this is where the Bohr radius came from, but the idea was the electrons were in these fixed orbits, and as you went further away from the nucleus, there'd be an energy transition. The problem with this idea was that it was based on classical physics, and no one could really understand why you wouldn't have an electron that sort of circled down and annihilated itself in the nucleus, because it should be attracted to the nucleus. So there were some problems around this time, but this is again in the early 1900s. But we got to remember Niels Bohr's two assumptions. If we now look at other things that were going on in chapter 1, we've come across the reduced mass multiple times in here. So it actually shows up in your textbook on in section 1.9. So that again will be on the exam. Also, very importantly, as we move historically towards quantum mechanics, we have de Broglie had his matter wave, and so it's important to know how to derive this. Here's the matter wave equation. So it's equal to Planck's constant divided by the momentum of the particle. What also does it involve? What it kind of comes from Planck's idea of quantized a photon, for example, E is equal to h nu, where nu here is the frequency. And we also bring in Einstein's theory of relativity, E squared equals mc squared plus pc squared. So we have to think about the momentum of a photon here as being equal to p times c. So E is equal to pc when we square these terms for a photon, or take the square root rather across this equation. So deriving de Broglie's matter wave is important. Historically we might say, well, yeah, if Einstein could have his photoelectric effect in here, which basically demonstrated that photons exist when they interact with matter, then de Broglie is basically saying, well, yes, there should also be a matter wave in here. So maybe matter acts like waves, just like light acts like particles. So that's what led this de Broglie matter wave led to the involvement of Schrodinger, who was a waves expert, and that's really how quantum mechanics was developed. Um, Heisenberg uncertainty principle is brought up in chapter 1, and it states that position and momentum cannot be specified simultaneously with unlimited precision. That's a cornerstone principle of quantum mechanics, and it basically tells us that it's all probabilistic. So any electron in an atom, we don't know where that electron really is. We can describe the probability of where to find it. That's the Heisenberg uncertainty principle. So that's what chapter 1 tells us. So as we move into chapter 2 of McQuarrie, chapter 2 is basically addressing how to solve wave equations by method of separation of variables. So wave equations are actually introduced, but the key here is to recognize the steps. And so those steps, very important to learn because they show up a lot in future chapters. But we factorize the function. So, many times we're going to find, for example, we have a function y that ends up being a function of theta and phi. And we see this later when we're dealing with the rigid rotator. And we break that down into a so-called theta function, which is only a function of theta, and a phi function, capital Phi function, which is only a function of phi. So this general idea is introduced in chapter 2. So we factorize that function into these new functions. So this is, what I'm saying here is we take this function y and we write it down in terms of functions of a single variable. So then we basically operate. So often we're taking derivatives, and so if we're taking a derivative with respect to phi, then obviously we can move the theta term outside of the derivative. And so there's an approach to doing that. That's really the approach that we're going to take a lot in this course. And so then once we've done that, we're going to divide throughout by the original function, and that allows us to come up usually with two terms. One term that's really, with our example here, is only going to be associated with the theta function. Let's do this in a different color. So only in the theta function, and one term that's only associated with the phi function. And so then of course we can solve that differential equation for each variable, right? So we don't we wait until we've separated the original function. So this is sort of multivariable calculus. We separate that into two expressions, and then we solve for each variable. So this approach comes up a lot. Where else does it come up? So it comes up when we actually think about the hydrogen atom. So this might be for a boron atom, which has 1s2, 2s2, 2p1, right? So the 5 electrons there are going to go into various orbitals, and so because there's multiple electrons, and because we have a Hamiltonian operator for each electron, and the Hamiltonian operator ends up being separable, we have this function, this trial function in here that we end up separating into 5 new functions, each one being for each particular electron. That's quite complicated to explain in a summary. But the examples that come up really in chapter 3 are very good examples. And so when we go from a particle in a one-dimensional box to a particle in a three-dimensional box, we start with this function in here. We've got an x function, which has is a function of x in here, and we have a y function. So we multiply these expressions together, and we also have a z function. All right, so that's what this expression is, and this ends up being the solution to the Schrödinger equation for the particle in the three-dimensional box. And so we can use the same ideas that come up here in chapter 2 of McQuarrie, using the separation of variables approach throughout the textbook. So The key point here is the separation of variables method is a stepping stone. You can expect a question or two on the final exam that is going to require you to know this. And I think it helps in our understanding of the course material if we can follow through the math. What it does is it allows us to break down solutions, for, as I mentioned above, the spherical harmonics into a theta function and a phi function. And later we're also going to find that for hydrogen-like atoms, so atoms with just one electron, we can break the wave function down into a radial function in here, and then the spherical harmonics here, which are functions, of course, of theta and phi. So by breaking it down, we can take quantum mechanics one bite at a time, one chunk at a time, and we can get our heads around it. Otherwise it becomes way too complicated. So that's chapter 2. Let's think next about what we covered in chapter 3. So let's just remind ourselves exactly what we're trying to do. Pull out your checklist for the course. Go through that checklist at the same time as I'm reading through these chapter summaries, and just make sure that you're understanding exactly what's going on with each of the points that I'm talking about. This summary is really not designed to explain everything to you, but to identify some holes that will help you go take a look and fill in the gaps. So let's get back to chapter 3.
So we now turn our attention to chapter 3 of McQuarrie, and we start to really delve into some of the key ideas of quantum mechanics when we move into chapter 3. What we're told up front, of course, is that the Schrödinger equation is in fact a postulate put forward by Erwin Schrödinger, but it does work perfectly to describe the nature of the hydrogen atom, as we're going to go on to find out. What we're also doing in this chapter is we're going to recognize the rules that basically allow us to start from a simple classical system. You've heard me tell you about these rules several times, and we're going to think about how to move to that quantum mechanical description. These rules, of course, apply very well for all solvable systems. And as I say, we've gone through this many times before. We describe the system classically. We substitute in quantum mechanical operators for each observable that we care about, or for each observable, in fact. We then build the Schrödinger equation. So, of course, we recognize that we're building this operator, and we're going to, this is an eigenvalue equation. We're going to solve that Schrödinger equation, and then we're going to go on to apply boundary conditions, which really means that we think about orthogonality and normalization in order to take perhaps an infinite set of solutions and turn it into one possible solution with a single constant in front. So this does bring up the idea of eigenvalue problems and what is an eigenvalue. So when we look at the Schrödinger equation, we do recognize that this eigenvalue is a constant. That's very important. Quantum mechanical operators, we're also told in this chapter, are linear. And here's an explanation of what a linear operator looks like. And they're also Hermitian, and we go on to find out the importance of Hermitian operators. And we might have if the Hamiltonian operator is Hermitian, then effectively we can swap these functions around, and that's more or less the issue with Hermitian operators, which we can't do unless they are Hermitian operators. So we also start to think about what a wave function actually is. What's the meaning of a wave function? And actually the square of that wave function is going to be the probability density of finding that particular particle at a certain point in space and at a certain time. We don't talk too much about the time dependence of the Schrödinger equation in this particular course. We tend to focus our efforts on the stationary state, but nevertheless there is a probabilistic interpretation where we can predict based on probability where that particle is and at a certain point in time. Chapter 3 also introduces us to the first simplest system that we're going to look at. That's the particle in the box. And really, the particle in a box is essentially an electron moving in a certain fixed space, and the potential is infinite outside of that box. So we know that the particle is inside the box, and the kinetic energy is pretty straightforward. We basically recognize that as equal to half mv squared. So it's the simplest system that we can think of, considering the electron as a particle. We do have these boundary conditions, and that of course means that the probability of finding the electron at x is equal to 0, or at x is equal to a over here, and that's a being the length of the box, that probability has to be 0. So those are those boundary conditions that help us find a single solution to the Schrodinger equation. So we have to first be familiar with this particle in a box example before we go on to apply these rules of quantum mechanics to more complicated systems. So I've actually again repeated those rules of quantum mechanics in a little bit more detail down in here, specifically for the particle in the box. And so, again, describe the system classically. I don't mind repeating myself a little bit here. Substitute in the quantum mechanical operators. Build that Schrodinger equation, okay, making sure that we know that arbitrarily, in fact, the potential energy of the particle is 0 inside that box. We solve that Schrodinger equation, and we recognize specifically which solution works. There's a couple of possible solutions. The cosine function solution or an exponential function solution won't work, and so we definitely need the sine function, which basically sine of x is 0 at x is equal to 0. So that's the key for the solution to this particular problem. So we apply these boundary conditions. As I mentioned earlier, we've got to have the wave function be 0 at positions x equals 0 and x equals a. As I've mentioned before, we've got to normalize our wave functions. The particle is, at the end of the day, inside the box by definition. And later on in chapter 3, we also talk about the three-dimensional particle in a box. And then we go on to talk about degeneracy. So there were some questions on the first exam about degeneracy. Degeneracy is basically the idea that for a single energy value, there might actually end up being more orbitals. There might end up being more wave functions that can provide a single energy that is the same energy. And we see this a lot with px, py, and pz orbitals, and we're going to use those as examples really now that we've made our way through the entire course towards the hydrogen atom. So that's really the summary of chapter 3, so we move along. Next up will be chapter 4 as we deepen our understanding of our rules of quantum mechanics. So now we're going to think about what's going on in chapter 4, and we start to deepen our recognition of how quantum mechanics is actually a set of postulates. But these postulates we're going to learn, these are kind of the rules of the game, and we need to be comfortable with them in our vocabulary as we move forward. So the first postulate then of quantum mechanics is in fact associated with the wave function that comes out of the solution to the Schrodinger equation. So the state of a quantum mechanical system, we are going to say, is completely specified by that wave function. So basically everything we need to know about the system is included in the wave function, right, which comes from classical description of the energy and the operators applied to it. And again, we just went through this for chapter 3. What's the meaning of the wave function? It's the wave function squared that is the probability density. So when we measure a probability density by a volume element, then we will end up with a probability given the limits of the integral. The second postulate that we care about is to every observable there is a linear operator. So it is a linear operator. We're going to find out it's also a Hermitian operator. We can look up these operators in table 4.1 of McQuarrie. And these would be provided on any exam typically, and of course in this case you'll have your equation sheet in front of you for the comprehensive final. In any so postulate number 3, in any measurement of the observable associated with operator A hat, so there's an observable A and we therefore have an operator A hat, the only values, so this is a statement, a postulate, the only values that will ever be observed are the eigenvalues. So these are the definite values that we can observe for that particular observable. And these eigenvalues, of course, must satisfy the eigenvalue equation. If we can't get single eigenvalues out, then, and this happens as we go to the hydrogen atom, for example, we might apply the operator for position, but we can't pull out a single eigenvalue for position because effectively the position is described probabilistically by that wave function. So sometimes we can't pull out a specific value, we can look for an average, and this is often associated with the probabilistic nature of quantum mechanics itself. But if we do see a definite value, a definite eigenvalue, we will be able to measure a specific observed true value. So here's our eigenvalue equation for that operator A hat, which is written over here. Okay, the second piece really is associated with the case where we might not have a definite value of A, in which case we can actually calculate the average value of A, and this is often called the expectation value, but more simply it's simply the average. Okay, and if of course we have a normalized wave function, the denominator here will be simply equal to 1, so we can kind of neglect it, but this is sort of the catch-all equation that says, you know, if we don't have a normalized wave function, then we allow for the average to be described fully by this equation, and so note the position of the operator inside that equation in between the two eigenfunctions. Okay, the next postulate. So the wave function does evolve in time according to the time-dependent Schrödinger equation, and that is found specifically in Chapter 4. And you'll note, of course, that we don't ever return to that in this particular course. It might become much more important as we think about the evolution of states, you know, maybe in conjugated polymers, energy transfer, and things like that, and maybe in spectroscopy it becomes more important. We also recognize the importance of the commutator. So if the commutator of two operators is non-zero, that means that the Heisenberg uncertainty principle means we can't know the values of the observables as pertaining to each of those operators at the same time. So, for example, you know, as we all know, we can't you know, the operator for momentum, the operator for position, those do not commute. So the commutator is going to be non-zero, and these two observables mean that they follow the Heisenberg uncertainty principle, and we can't simultaneously know accurately the momentum and the position of the electron at the same time. In Chapter 4 also there's another description of the importance of orthogonality. Orthogonality simply means, you know, if we have a bunch of orbitals, you know, let's actually say we have this makes some sense to us now as chemists, a 1s orbital and a 2p orbital, for example. We can't have an electron in both of those orbitals at the same time. That single electron and the wave function for that electron in 1s would be orthogonal to the wave function for 2p, because that electron cannot be in both orbitals at the same time. And that's the basis for this idea called orthogonality, which carries through throughout quantum mechanics. Hermitian operators, as I mentioned before in the prior section on chapter 3, Hermitian operators are talked about more in detail in chapter 4. And essentially that allows us to move wave functions around such that if we have a Hermitian operator and we have two wave functions here, we can effectively switch them around such that the complex conjugate sits on the B wave function rather than the A wave function. Much more to it than that, but basically described in chapter 4. And so that's chapter 4 is kind of our gateway. It tells us about the rules of the game, so to speak, and then we're going to move on to look at harmonic oscillators and rigid rotors, and eventually the hydrogen atom as we move into chapters 5, 6, and 7. So welcome back to the summary of McQuarrie's quantum mechanics textbook. We're going to talk now about chapter 5, and now we take a little jump. We start to think about a simple mechanical system such as a ball on a spring connected to a wall. We remove the idea of gravity and we just have that spring moving backwards and forwards. And we're familiar with this from Hooke's law description of that particular system. It's very similar, of course, also to a little girl on a swing, with that girl sort of swinging backwards and forwards on that swing, where she starts at a high potential energy, moves forward through the equilibrium point, which has a maximum kinetic energy and minimum potential energy, and sort of moves back up to a point where she has maximum potential energy and minimum kinetic energy. So this is also very familiar to us in the real world, even if we don't see balls on springs bouncing around every single day. But there is a force constant that's associated with the spring, and there's a reason we look at the spring. It's very similar to the chemical bond, in fact, between two atoms. And so either way we look at this, energy is conserved, and that means that potential energy is converted into kinetic energy and back again as the two balls, or as a single ball moves backwards and forwards, or as a girl on a swing moves up and down. With that in mind, we quickly recognize that in fact the diatomic molecule is like a harmonic oscillator for a single mass connected to a wall, and then we get the opportunity to use the reduced mass that was introduced earlier in the textbook. So we also then start to think about how with a diatomic molecule, the potential associated with a diatomic molecule, true diatomic molecule, is described with the internuclear or Morse potential, and it has some overlap with the Hooke's law potential energy, but it's not exactly the same. So the math chapter that precedes this chapter talks to us about a Taylor series expansion, and that allows us to provide an approximation to the Hooke's law description in terms of a series expansion. And then later we can apply some anharmonic terms to kind of better describe the system as it's described using the Morse potential. And this is again we had some discussions in class on this. This is well described on page 217 of the textbook. The Schrödinger equation is then developed. Of course, now we have a potential energy and a kinetic energy. Potential energy is described with Hooke's law. The kinetic energy is described with, again, half mv squared and some Newtonian mechanics. And in the next section of this textbook, we actually don't see how the equation is solved, but we are provided with some eigenvalues, and we start to look at the results. We introduce the idea of a selection rule, so we start to plant some seeds about selection rules, and we've told that the change in energy, which is equal to the photon energy in spectroscopy, is equal to the energy of a vibrational state that's higher by one quantum number than the state below it, right? So if we want to add a photon to the system, if the system absorbs that photon, we're going from a quantum number of, let's say, 0 up to a quantum number of 1. So these energies are associated with now quantum numbers, and the energies are a function of those quantum numbers, and so these quantum numbers come out of the mathematics. We're told about the overlap with spectroscopy. There's a force constant in here, which is more or less, gives us the frequency of oscillation that we see in an infrared spectrum, for example. So we're kind of encouraged to think about how this particular branch of quantum mechanics connects with infrared spectroscopy. We're also encouraged to recognize that it's in fact a changing dipole moment that's important, since we have an oscillating electromagnetic field. How does that oscillating electromagnetic field interact with matter? And we have to have a changing dipole moment in order for that oscillating electromagnetic field to interact. We kind of punted a little bit in this particular course on infrared activity in polyatomic molecules, and this is on page 233 to 236. Unlikely to be any exam questions on that in the exam, because we did not cover that fully in class. Now we start to look at the wave functions themselves. So this is now a much more complicated solution to the Schrödinger equation, and we do not go through the math that takes us to those solutions. In fact, what's happened is we're told that Hermite polynomials actually lead us to these wave functions. We start to look at what those solutions look like. We have a function. And we're basically encouraged to consider, for example, this is the case with v is equal to 1, what that wave function looks like. And rather than focus on how the Schrödinger equation was solved, so we also can plug those functions into the Schrödinger equation and work it through and operate on that wave function, just to prove that it is indeed an eigenvalue equation. It does give us an eigenvalue that is a constant and is the energy for that system. We talk about very briefly the idea of tunneling, and the idea of tunneling basically tells us there's some possibility, there's some probability, in fact, that the expansion or the extension of the bond is actually greater than what would be expected classically. And so this is a bit of a very unusual, and it's hard for us to wrap our heads around this. But tunneling is also something that's very important. It basically says that there's some probability that an electron in a molecule may actually reside at a position outside of the actual molecule, so it's almost like saying for a particle in a one-dimensional box with high but not infinite potentials outside the box, there's some probability that that electron may actually jump outside the box, even though it doesn't have the energy to overcome the barrier. That's really what tunneling is. Okay, so look that up in your textbook. We're also told about the correspondence principle, which basically says that the higher the quantum number we go, the more close the system resembles the classical case. So as the quantum number for vibrations goes up, we start to see more probability, in fact, that the system resides at the point of highest potential energy, kind of similar to the point where, again, this girl on a swing, it's very likely for that girl, if you stop and take a photograph at any one time, the most likely position is where the girl is at the point of highest potential energy. So when quantum numbers go high, we end up having quantum mechanics look very similar to classical mechanics. We were introduced to the ideas of odd and even functions. Why do we care about that? Those things are important because they actually simplify the mathematics, so well worth a review of that. It may save you some time in the exam. We also start to understand that the more nodes there are, the more 0 points. So here's a node in the wave function where the wave function crosses 0. The more nodes, the higher energy the system is, and we're going to see that consistently as we move towards hydrogen atoms. So as I said, these rules for odd and even functions help us simplify, I should say simplify the calculus. And we're also introduced to some recursion formulas that start to illustrate and demonstrate how those selection rules that seem very abstract, how they fall simply out of the mathematics. And these are properties of Hermite polynomials. Where did Hermite polynomials come from? Often these mathematics, these mathematical solutions were developed before quantum mechanics came along, and so the pioneers of quantum mechanics could simply dip into the mathematics that was there long before the application came about. So that's chapter 5 for us. Again, it's a slight stretch beyond the particle in a box, and again, it's for the first time we don't see how the Schrödinger equation is actually solved. We're provided with the wave function solutions, and we're kind of asked to plug them back into the Hamiltonian operator and see what we get, and demonstrate that our Schrödinger equation is indeed valid. And it actually does match with experiment, and it helps us understand better the spectroscopy that we use to fingerprint our compounds that we make in a synthetic chemistry lab.
Well, sorry about that. A lot of noise in the background. I wasn't in my usual studio. Hopefully that'll prompt you to work hard and focus on what you're trying to hear, again, as you go through the rest of the material there. So I'm going to stop on this particular video, and we'll look at chapters 6 and 7 and beyond in the next video. Thanks for your attention.